Good morning, good afternoon, and good evening, everybody. My name is Jamie Coleman, and today I'm here to talk to you about some simple tweaks you can do to get the most out of your JVM. So again, my name is Jamie Coleman. I'm a developer advocate for IBM, and I generally specialize in container technologies and microservices, all based around Java. So let's get started. So what we're going to be looking at today, we're going to be looking at why the JVM is important for Java developers, how the cloud has changed generally the characteristics of today's JVMs, and then we're going to look at some of the most popular JVMs and give some comparisons. Then I'm going to move on to how you can pick the right runtime for your JVM, because having the best JVM in the world doesn't mean anything if you have a runtime that's not utilizing those characteristics. Then we're going to get onto the part where we actually talk about tweaking your JVM, which is kind of the main point of this presentation. I'm going to talk a little bit about Open J9 and what class cache sharing is, and hopefully provide you with a small demo today. I'll talk briefly about what Open J9 idle tuning is, the Open J9 JIT server, and a new technology which could really revolutionize how JVMs work. And then finally onto a small recap at the end. So, why is the JVM important? Well, without it, as Java developers wouldn't have anywhere to run our application code. So what is a JVM? It's a virtual machine, and it's basically responsible for taking your application's bytecode and converting it into a language that the machine understands, so machine language here. Most other languages compile specifically for a specific system, but the whole point of Java is the compiler converts the code for the Java virtual machine that can be used anywhere, hence the phrase, write once, run anywhere. So, why do people use JVMs? Well, JVMs are great because you have cross-platform support. So again, like I mentioned, it will run anywhere. A massively large ecosystem library. I mean, Java's been around for a while, so there is loads and loads of different libraries you can utilize. It has one of the best garbage collectors out there for different programming languages. It's got really powerful monitoring tools, and it is proven and robust. Okay, so I'm not going to go too much into detail here about what a JVM, how it works, but this is kind of the architecture of a JVM. So you kind of have your ClassLoader Subsystem on the top, then you kind of move down to the runtime data area, and then you've kind of got your execution area. So what do those different things do? So the ClassLoader Subsystem, so the loading part of that, loads classes using 3 different class loaders, and that's the Bootstrap class loader, the extension, and the Application ClassLoader. The linking part of this basically verifies the generated bytecode and prepares all the static variables and assigns default variables and resolves all symbolic memory references. And then the initialization part essentially assigns static variables where their original values and executes to the static block. Okay, moving on to the runtime data area, and again, I'm only going to give you kind of a brief overview here of what a JVM does, but you've got your method area, which, as it says, stores metadata, constant runtime port, and the code for your methods. Then you've got your heap, which is used like a common memory shared place for things like multiple threads, stored objects, instant variables, and arrays. And then you've got your JVM language stacks, and these are kind of built for local variables. And then you've got things like PC registers. So every thread essentially has its own registrar, and it stores the address of the Java virtual machine instructions, which it's currently executing in these registers. And then, of course, you've got your native method stack. This holds native method information. So for every thread that is created, there's also a native method stack that is created. So, and then finally onto the execution engine. This is the part that actually does some of the work. So essentially, the execution engine is made up of the interpreter and the JIT compiler. So the interpreter interprets the bytecode faster, but executes quite slowly. So the disadvantage of an interpreter is that when one method is called multiple times, every time a new interpretation is required. Compared to the JIT compiler. Now, the JIT compiler neutralizes the disadvantages of the interpreter. So the execution engine will be using with the help of the interpreter in converting bytecode, but when it finds repeated code, it uses the JIT compiler, which basically compiles the entire bytecode and changes it to native code. And native code executes a lot faster than custom code, so this is why we use the JIT compiler here. Okay, so out of the nitty and gritty bits of the JVM, so how has the cloud and cloud technologies changed the way we look at JVMs? Okay, so if you think of cloud computing is equal to money. So we try and save We try and make our applications as small as possible and try and utilize the resources we have because we don't own that hardware. We're paying for every bit of resources we need. So essentially, if you think about it like this, so as a developer, I don't care so much about my organization saving a bit of money on the cloud. But to put this into terms of what we might think about is energy. So every time we're creating applications that are not efficient, not only are we wasting money, but we're wasting energy. These data centers, they consume massive amounts of energy, and we really need to think about what we're building and where we're putting it and how we build it. Because if we don't, not only are our organization, our executives going to get angry at us for spending money that isn't needed to be spent, but we're also going to save a bit of energy as well. So what the cloud offers, so imagine this chart. Essentially, the light blue area, this is your data center, your local data center, and the light blue area are resources you never need. So with your data center, you always have to have the resources for peak load. So that could be, a special holiday around Christmas time when people would buy more things online. So you've got to basically have that hardware there all the time. And it's wasted money, it's wasted hardware. Most of the time, it's not going to be used. Now, if we move to the cloud, we take our applications there, and you can see we're freeing up that extra bit of hardware which would normally be sitting in our data center not doing anything, and we're allowing other people to use that. So not only are we not paying for this hardware now, but other people around the world can then utilize it. So again, back to the thing I was saying, saving a bit of energy. But now if we change our applications to this kind of cloud native approach where we build microservices or functions as a service, we have more granular control over our applications, which means we can scale them quicker, scale them down quicker. And again, we can free up more of these resources because we're only buying smaller units for other people to use. Again, saving money and hopefully saving some energy. So I always find the problem with Java and microservices is it's great, but you have the overhead of a JVM. So you have to put this JVM in every one of your services because your application code won't run without them. And you then have this overhead of the JVM in lots and lots of different services. So that's when a lot of producers and creators of JVMs kind of went back to the drawing board and they had a look at the metrics that they were really that were key to kind of getting a good balance for using on the cloud. So of course, stuff like startup time, footprint, ramp up time, response time, and CPU usage are all important. But when you change the characteristics, when you change one of those characteristics, it can have a detrimental effect on the others. So getting that right balance is very important, and that's what a lot of people are striving to do, especially in this new cloud native world. So who remembers this phone? It's a great phone. I remember the battery used to last a week, probably because it had a very, very small, tiny JVM inside, which was cool. But this, so the characteristics for this phone and the Java that ran on this phone are very similar to what we expect from the characteristics of JVMs in today's society. So, for example, small footprint, fast startup time, and quick immediate ramp-up time. Because, for example, if you wanted to make a call on this phone, you didn't want to have to ramp up the calling app to make that phone call. You want it just to be available there. So if we compare these to the requirements we have in the cloud, they're pretty much the same. So small footprint, fast startup, and quick and immediate ramp-up time. Now, the reasons have slightly changed. The reasons before were because the hardware literally could not it wasn't powerful enough to do what we do today. Whereas now that's not the case. We have pretty much very powerful hardware. We just want to utilize as small amount of it as possible to save money. So back to the whole point of, it's okay. We don't, as developers, shaving a few dollars off here for our application running in the cloud isn't going to make really much change to our life. But as developers, we should be thinking about this in another way. So going back to the whole energy thing. So there's over 500,000 data centers in the world, and the land they consume is equivalent to around 6,000 football pitches. So it's a lot of land. Now, currently, if you take the United Kingdom's energy consumption and you times that by 1.5, that in 2019 was the global data center energy consumption. And that was in 2019. I presume it's probably more like 2 times the UK's energy consumption these days. But that's a lot of energy that is being consumed by these data centers, which nobody can see. So if you look at this graph, now luckily hardware engineers have saved the day for us. They've done their part, because if we carried on current trends in 2010 with the same hardware, we would now be using a lot of electricity in these data centers. But luckily, the hardware engineers have done their part and they've created some amazingly efficient hardware which have cut that trend down dramatically. Now, what we should be doing as software engineers is doing our part and getting our applications more efficient so we can also help curve that trend. Right, so that is why I think as developers should be thinking about this a little bit more. But let's have a look. There are JVMs for kind of everything you need. So if you want to build stuff on tiny little Arduinos, there are JVMs for that. And as you can see, there's some great names for JVMs here, like Wonka JVM, Squawk JVM, and they all do lots of different things. So there's one here called the Maxine JVM, which doesn't get talked about a lot, but if you've ever used the Graal VM, that is based on the Maxim JVM, which was created, I think, at Manchester University in collaboration with Oracle. But at the time, they didn't see it as being useful. Cloud-native technologies hadn't become a thing yet. But as these kind of cloud-native characteristics have become more important, Oracle went back to this project and reopened it and essentially turned it into what is Graal today. So these are just a few of the most popular JVMs. Of course, you've got Oracle's JVMs. All the open source JVMs are the ones I like to advocate for. Open J9, which I'll show you some of the functionalities today. But of course, people like Amazon, they have their own flavor of JVM, which really is just Open JDK builds, which Amazon have built and support. So these are the three main JVMs I'm going to talk about. So of course, I can't not talk about HotSpot, originally released in 1999. By Sun, which is now Oracle. And this JVM was really good. So in 2006, this was completely open source to the community, which was amazing, which paved the way for projects like OpenJDK. So people could go and build their own JVMs and change the functionality, change the characteristics, and make it more kind of cloud native. So HotSpot is called HotSpot because what it does is it continuously analyzes the program's performance for hotspots, which are executed often or repeatedly. And what it then does is it targets those hotspots for optimization. Basically, yeah, so that's kind of where the name HotSpot JVM came around. So Open J9 is IBM's JVM. We open sourced this, I think, about 4 years ago now, maybe 5. This was open source with Open Liberty, and this was IBM's biggest open source contribution in history. It was millions of lines of code. And Open J9 is an amazing JVM. So not only is it used by some of the biggest corporations in the world, so it's very, very robust, but the Open J9 team have kind of gone back to the drawing board to look at the characteristics of this JVM to make it more cloud native. And I will talk you through some of those technologies in a moment. But if you just compare, for example, Open J9 to HotSpot, you can already see the startup time is 50% faster, which is what we need when we're ramping and scaling our microservices. We want a smaller footprint after startup. I mean, we don't want our JVMs using lots of memory. We want to try and get them as small as possible because, like I said, with Java, they're more of an overhead. We have to have these in every service, so getting that footprint is small is good. Ramp up time. We don't want, say, if all of a sudden we get loads of traffic to our services and our services take, a couple of minutes to ramp up and scale up. We want that to happen instantly because otherwise people's requests are going to get denied and people are not going to have access to the service and probably stop buying our product. So you want to make sure that everything ramps up quickly. And again, a smaller footprint under load. So it's all very good having all these microservices, but again, we're trying to make very small services here. So we want them to handle as much throughput as possible and use the smallest amount of resources as possible when under load. And the good thing about that is if you're using, say, a JVM that uses half the resources under load, hopefully you'll need half the amount of microservices, cutting your costs down and the amount of energy you use. So Graal VM is the last one I'm going to mention, and I'm going to mention it because it's very talked about JVM these days. It came around in 2019, and the goal really around Graal was to kind of create a JVM with the characteristics that we expect from cloud-native development. Now, since this has come out, a lot of other JVM kind of builders have taken these characteristics on board, but Graal VM does some unique things. So what it does is it basically compiles its code generally down to native code, which is, as I explained when I was talking about JVMs, native code executes very, very quickly. Now, this does have some problems. Sometimes performance issues under load can be a problem, so throughput might not be as high. So there are lots of different issues with this. Some Java EE or Enterprise Java or Jakarta EE now specs might not work with this because, again, everything has to be compiled ahead of time. So this can have detrimental effects on your application. But really, again, the whole goal of this, and like I said, it was based on that project created in collaboration with Manchester University in the United Kingdom, to kind of get us to a place where our JVMs, or where we're running our applications, aren't a bottleneck or an overhead. They do what we expect in a cloud-native runtime. So picking the right runtime. So it's all well and good as having a JVM and tweaking it and get the most out of it. But if I go and run a runtime on top, which is absolutely huge, then I'm not going to get the benefits of what I'm trying to achieve by tweaking my JVM. Now, of course, you can do these tweaks to non-kind of cloud-native applications like big monoliths, but where the characteristics fit most are things that are cloud-native, so microservices and functions as a service. So on to Open Liberty. This is a completely open source runtime, and as I said, IBM open sourced this with Open J9 about 4 years ago, and this is really built for kind of cloud-native technologies. So we've taken a focus on developers, so it's just enough application server. We don't want it to have everything. We want it to just do what it needs to do for our needs, so it's not going to be too big. We've got tools and technology like dev mode, which help you, code really quickly without having to keep restarting the server, etc. And things like zero migration make it, moving from an old version of a spec to the latest version of a spec easy. And things like it's optimized for containers, designed for DevOps, and very good efficient memory usage, which I'll talk about in a little moment, and fast startup, etc. So again, like I mentioned, it's just enough application server. So rather than having this huge application server that's gigabytes and doesn't scale very quickly, you just include the functionality and the features you need, and that allows it to be very small and scalable. In regards to API support, we've really been on the forefront in two of the main kind of APIs that are around. So we have been the first to deliver microprofile version 1, 2, 3, 4, and now 5. And we've also been the first to deliver Java EE8, Jakarta EE8, and now Jakarta EE9, I think, about a couple of months ago. So our developers have worked very, very hard to make sure those specs are working, and they work with Open Liberty. So I can't not mention Quarkus. Quarkus is a runtime by Red Hat, which is really built, again, for this kind of cloud-native technologies. So similar things, very small amount of configuration. It does native execution, so this works with GraalVM, and it supports loads of libraries, such as things like microprofile, like I mentioned with Open Liberty. So if you look at a bit of how the startup time and things, using Quarkus and GraalVM, you're automatically looking at a startup time of 0.01 seconds. And that is really fundamental when we want to scale in this kind of cloud-native environment. But like I said, using native code can have its problems, so just be aware of picking the right runtime for your needs. And of course, there's lots of other runtimes, as you can see here. So do your research into each one of the runtimes and find the best one that suits you. And also with containers in this cloud-native world, you don't need to stick to one runtime. You can have lots of runtimes all talking to each other, all in different containers. So do bear that in mind. So onto one of the main parts of this presentation, which is tweaking the actual JVM. So what do I suggest when I want you to get the most out of your JVM? So number one, writing efficient code. That's the most important thing that all of us developers can do. It's very easy to forget about that. And I'll talk about some of the things you can do there. Again, picking the right JVM for your needs. There's lots of different JVMs. They all have different characteristics. So making sure you pick the right one is important. Pick a runtime that's right for your application. Like I mentioned, there's no point having a runtime that's gigabytes in size if your application's 10 megabytes. It doesn't really make sense. So make sure you pick what is right for your application. Use profiling, and I'll explain a little bit about what that is afterwards. And then, of course, JVMs have lots of different things you can do to them. So tweak your JVM depending on your needs. Now, your development needs may not be the same as your needs in production. So, for example, I'm going to be talking about some things that I would probably use as a developer, but I might not use in production, and vice versa. So do take that into, do think about that when you're thinking about what tweaks you want to do, because you might not want to do some things in production that you might want to do locally. So writing efficient code. Use primitives where possible. So another way to avoid overhead and improve the performance of your application is, like I said, to use primitive types and their wrapper classes. So it's better to use, for example, an int rather than an integer, or a double rather than a double with a capital D, because this allows your JVM to store the values in the stack instead of the heap. And this would reduce memory consumption and basically allows your JVM to handle that type of object better. Use a string builder rather than a string buffer. This is a lot more efficient than a string buffer, but just bear in mind a string buffer is not thread safe, so it's not always good to use these. So again, make your own decisions if you need it to be thread safe. Avoid using iterators. They're not very good. They're very resource heavy, so try to avoid those. And avoid using things like big integer and big decimal. If you don't need a big integer and a big decimal, there is no point of using that variable. It's just going to consume more resources in your JVM. So if your application doesn't require such a big number, don't use it. It'll make your code much, much more efficient. Using the right JVM for your needs. Like I said, there's lots of different JVMs out there. So, of course, you've got OpenJDK, you've got things like HotSpot, Open J9, and Growl. So look at what you're trying to do with your application and pick a JVM that suits your application. Back to picking a runtime that's right for you. So this is a graph I created. It kind of shows where some of the different runtimes I've talked about fit. So Web3 Application Server, very good application server, and we have customers that have been running, say, Web3 Application Server non-stop for about 15 years without shutting it down or doing anything. So it does what it needs to do, but it's quite big. It's like 4 gigabytes in size. So if you wanted to use this for microservices or even what I would consider a macro service, it wouldn't be very efficient at scaling up and down. I think, the startup time could be up to like 8-10 minutes. So, if you've got customers coming in trying to, hit your endpoint and all of a sudden it takes 8 minutes before you've got extra resources to handle those customers, they're not going to be sitting there trying to hit your endpoint anymore. They would have gone. So you really need to pick the right runtime for this. OpenLiberty is great because it has a startup time of just over a second, so really good for microservices. But it also fits into this weird area of a macro service and a monolith. So you can use OpenLiberty for a monolith. That's absolutely fine. It has pretty much all the functionality Web3 Application Server does. But it also fits in this macro service area. And a lot of people say, is that just a distributed monolith? And I'm like, no, that is just what I would consider a distributed monolith is a well-architected monolith. Whereas a macro service, I kind of find it's the state that people get to when they've got a monolith and they're trying to break it into microservices. And then they basically realize some of their services are so highly coupled that it doesn't make sense to break them apart anymore. So then you kind of get these slightly bigger services with all the kind of things that are highly coupled together, but it still means you can scale individual parts of your application rather than having to scale the whole monolith and the whole application. Profiling is really good. So Java profilers are really useful, and they basically enable you to monitor all the Java bytecode and all the operations that are going on inside of your JVM. So this includes stuff like your garbage collection, so you can see what's going on in there, object creation, method executions, iterative executions, and thread executions. And it is, honestly, try some of these profiling tools, because if you try them, like JProfile, YourKit, etc., it's quite amazing to see all the stuff that's going on inside your JVM, which generally as a Java developer, I don't even consider even thinking about that. But if you're scaling up and you're building a bigger application, it is probably worth looking into exactly what's going in under the covers inside your JVM. And tweaking your JVM. So kind of what we were talking about. So tune your garbage collector. There's lots of different ways you can do this, so you can make them more efficient. Use things like the at-in-time compiler to help your applications boot up quicker. Class cache sharing is available on HotSpot and Open J9, and I'll hopefully show you a demo a little bit later and how that works. Enable idle tuning. So this is quite a clever technology that if your service isn't doing anything, if it's got no requests, then it shouldn't be using the same amount of resources as if it was handling loads of requests. So idle tuning basically allows your JVM to save you a bit of memory, a bit of resources by when it's got no requests, it kind of just idles a little bit. So yeah, save some resources. The JIT server is really cool. So it basically allows you to do compilation on a different machine. So technically, you could put your JIT server on a cloud, you could put it in a different container, and it basically allows you to spread the load of your JVM's compilation, which is very cool because if one of your services is struggling under load, the JIT compiler can take over that and then basically relieve it of some of its stress. And again, start with a small heap size. Now, this can be difficult to do because you've got to be careful. If you start with too small and your application requires more, it'll just break your application. But I generally find it's good to start with something small and then just gradually increase when you need more, rather than just providing with some massive heap size, which is going to consume lots and lots of resources. So Open J9 class cache sharing. So we're going to get onto the demo I wanted to show you in a minute. So what is this? Essentially, it allows you to kind of take all the classes you use at startup that are constantly used lots and lots of times and put them into this kind of shared class cache. And this survives longer than the life of your machine. So if you reboot your machine, that cache will still be there. It can't grow in size, but you can, and when it becomes full, that's fine. It just stops adding new classes to it. But you can set the size if you want to. So how does this kind of work? So with a normal JVM, you generally have your ClassLoader cache, your parent, and then your file system. In contrast, a JVM running class cache sharing has the ClassLoader cache, the parent, then the shared classes cache, and then the file system. So it's got this extra step to load all the kind of classes you use all the time on startup, rather than using the file system and having to find all those classes there. So it's really, really simple to get started with this, and I'll show you in a moment how to do it with OpenLiberty. But basically, you just have to declare a JVM options, and in this case, it's just -x share classes. You don't have to put the name. If you put the name, you can have different names for different applications on the same JVM. But yeah, that's all you need to do is set that JVM properties file, and yeah, it will enable this. So this is a comparison. So this is OpenLiberty startup time using the HotSpot JVM without any class cache sharing enabled. So you can see we're just over 2 seconds. If we look at TomEE, it's about 4 seconds, etc. Now, if we use Open J9 with OpenLiberty with shared class caches, you can see our startup time is now about a second. Now, we also enable this on all the other runtimes. So I'm not saying you have to use OpenLiberty to take advantage of this. Even TomEE, which is quite a big application server, has nearly lost a second. So I'm not trying to advocate all this stack and all these technologies, but taking just one of these and applying it to what you currently have could save you a lot of resources. I mean, imagine if everyone around the world who's running Java applications, which is probably a lot of people, did these tweaks and, took a second or took half the amount of time to start up. How much energy and resources we would save around the world would uncomprehendable, I'd say. And then again, same with containers. So obviously it doesn't have the same effect, but OpenLiberty in a container starting about 6.5 seconds with this functionality enabled, just over 2 seconds. And again, I want to get back to the point that if all developers around the world utilize these kind of technologies, we could save a lot of resources. And we have a lot bigger improvements over some of the other runtimes. That is because we've worked with the Open J9 team to put improvements in not only Open J9, but also in OpenLiberty to kind of optimize it for this cloud native world we live in. Right, so now I'm going to show you a quick demo. This is fully interactive, so you can literally just go to this URL or go to the OpenLiberty guide site, click on one of the guides and click Run in Cloud, and you can actually follow along and do this demo at the same time. Right, so let me get my environment open, which should be here. Yep, I'm still here, I swear. Okay, so what we're going to do, we're using this because it has a sample application that we can just get going with very quickly. So if you just go to, say, step 3, just clone down the repository we're going to use today. Okay, navigating to that repo. So I'm going to go into the finished directory here because that has the completed code we need. Right, what I'm going to do is I'm going to launch OpenLiberty, just normally with Maven. Then I'm going to enable class cache sharing, launch it again. Now, the first time you launch your runtime with this enabled, it has to populate the cache because there's nothing there. Then I'll shut it down, and then hopefully, pray to the demo gods, you will see a massive improvement in the startup time. So let me first just get Liberty running, Maven Liberty run. I'll hit enter, and while that's doing that, I will show you very simply how to enable class cache sharing. So with Liberty, we have a Liberty configuration folder here. This is where we put all our configuration in for different things. I'm going to create a new file called jvm.options. OpenLiberty passes this file in on runtime, so basically anything that's in here, it will set that as the JVM properties. So I've created that file, open that. So the commands I need is x-x shared classes. Okay, right, so just wait for a moment. We're just going to wait for OpenLiberty to boot up. Once it's booted up, I'll shut it down again, save this file, and then we'll boot it up again so the shared class cache can be populated. It'll take a bit of time the first time because obviously it's got to download dependencies from Maven, but it should be a bit quicker afterwards. So as an example, so far, without me doing anything, OpenLiberty has started up in about 10.3 seconds, okay? So I'm going to shut that down. I'm going to save this file here, and then we're going to boot up OpenLiberty again. So on this run, it's going to populate the shared class cache, get everything ready. So the next time we boot this, all those classes we use on startup that we use quite often will be there and ready, and it should boot up a lot quicker. So first run, 10 seconds. I presume the second run will be about the same or maybe a little bit less. So we've got 7 seconds here. But now our cache is completely populated. So if I run this start command again, praying to the demo gods, we should hopefully see this start up in a much quicker time. And again, all I've done is added 1 line of code to my command, and look, we've started up in 2.01 seconds. Now, imagine if every developer around the world made this simple tweak to their JVM for all their application code and brought their application startup down from 8 seconds to 2 seconds. We could save a lot of resources, and it would help you basically take advantage of these kind of technologies that have been embedded into our JVMs for the last 5 years to really make the most out of your applications. Right, I'll go back to my presentation, and I will just quickly finish talking about some of the other technologies in this JVM. So idle tuning, I mentioned it very briefly before. What is idle tuning? Essentially allows your JVM to save some resources when it hasn't got any requests going to it, because why should it be using the same? So as you can see here, we've basically got points where it's not much memory is being used, and the JVM, as you can see, has gone idle. It's saving some resources for us, which is really useful. Again, trying to save some energy around the world. Again, with the JIT server, you basically you have all your you can have the JIT server in different places. The great thing about this is under loads, it means your JVM will keep working. So we've got 3 graphs here. The first graph is basically the Open J9 JVM with basically not under load, but unconstrained environments with 300 megabytes of space. Now, the second, we've got Open J9 with the JIT server and without the JIT server. We move that down to 256 megabytes. As you can see, without the JIT server, the JVM is starting to struggle a little bit, but fine, the throughput is still good. But then if we constrain that down to 200 megabytes, without JIT server, the JVM has literally hit the floor. It doesn't know what to do, it doesn't have enough resources, and it's basically hardly got any throughput. But with this JIT server technology enabled, you can see the throughput of the JVM is still going. It's still going strong. Not quite as strong as obviously if it had a lot more resources, but it's still doing what it needs to do. And then as a developer or an ops person, I can say, oh God, we haven't put enough resources into this, but thankfully the JVM is still going. Now I can give it some more resources, disaster over. Where without this JIT server technology, your container would have just fallen over, your microservice would have just fallen over, and your customers won't be able to use your application. Really simple, again, to enable the JIT server. Again, it's just you pass these requests on the command line, and it just sets up your JVM as a JIT server. So very simple to do. Right, so we've got I've talked about lots of these existing technologies, JVMs and different things there. But what about any future technologies? Is there anything coming along that could, help the JVM be more kind of cloud native? So there's this technology called CRIU, which stands for Checkpoint Restore in User Space. And it's a really good potential solution for basically really fast startup time. Now, this technology has been a feature on the Linux operating system for quite a long time, but nobody's actually used it for running applications. So essentially what it does is it takes a checkpoint, and what you can do is your checkpoint could be just before startup or just after startup. And then what it can do is revert to that checkpoint, starting you up straight away. So for example, we've been playing around with this with OpenLiberty and Open J9. And as you can see, the bigger the application, the more benefits you get from this. So a small application that normally takes about 1.5 seconds to start up, with this technology is now starting up in 0.2 seconds. But if you have a bigger monolith application that takes 4 seconds to start up, the benefits you're going to get will be even higher. Yes, it's 0.5 second startup time, but going from 4 seconds to 0.5 seconds, that's a massive savings in startup time. Now, there are problems with this technology which developers are trying to solve. So lack of encryption, for example. Problem is, running as a non-root user is one, so developers don't like to be run as root users in containers, and that's something that this technology is kind of demanding, so trying to get around that. Predictable random number generators can be difficult, but there is another library you can use to circumnavigate that. And essentially, there's kind of no APIs around for any of the runtime to kind of handle this technology. But in the future, this could be very, very useful. It is being developed, and it could really take, for example, non-native Java application codes, so normal Java EE or Jakarta EE or microprofile code, and run it without having to compile it to native code. So then you get all the benefits you'd normally have with not having to use native code, but starting up in similar times to using stuff like GraalVM. So there's a bit of a recap, what, if anything, you've learned today. I hope you've taken something away from this talk. Firstly, what I want you to take away is write efficient code. We're developers. It's our responsibility to create code that advances the world and makes it more efficient. So again, first and number one, write efficient code. Use the right JVM for your needs. Don't just use it because your organization have been using something for a long time. Pick the right JVM, which is really useful and will give you the characteristics you need for your application. Pick the right runtime for your application. Again, making all these tweaks and having a very cloud-native JVM is not going to mean anything if you've got a humongous runtime running on top of it. Use things like profiling, actually look and get intrigued at what's going on inside your JVM. And of course, tweak your JVM. Do changes to your JVM, make changes to it to make it run more efficiently for your needs, because at the end of the day, less money is also equal to less energy. And hopefully, as engineers, it's our responsibility to try and save as much energy as we can on the cloud. Here's some links to some useful information about some of the different JVMs, some of the different runtimes, and also some documentation for where I got some of the information for this talk from today. And again, here's some more references to some of the information in regards to energy consumption and things like that. There's loads of information out there, but trailing through the internet can be difficult, so all the links are there for you. And that's it from me. I'd just like to say a thank you, and if you have any more questions or anything like that, please do not feel scared to reach out. I'll be more than happy to answer them. Thank you.